Part 4, questions 31 to 40. Question 31. The compounds shown are all produced by plants. Each compound is warmed with acidified potassium dichromate. Which compound will give a different observation to the other three? Now, acidified potassium dichromate is a strong oxidizing agent. Okay, so it is going to oxidize this primary alcohol first to the aldehyde, okay, then later to a carboxylic acid. So this one will give us a carboxylic acid, this one will give us a carboxylic acid, even this one a carboxylic acid. But when you look at this one here, D, this one is a tertiary alcohol. We see a group here, a group here, a group here. And tertiary alcohols are not oxidizable, okay? So we can see that here we are not going to receive any oxidation. So this one will change from orange to green. So there is orange to green here, even here, even here, because oxidation has taken place, but not here. So that means our answer here is going to be D, okay? Because tertiary alcohols are not oxidized. Question 32. Structure and stereoisomerism should be considered when answering this question. They are saying how many alcohols with the molecular formula, this one here, give a yellow precipitate with alkaline iodine solution. Now, with alkaline iodine solution for alcohols, for this one to give us a positive, for an alcohol to give us a positive test with alkaline iodine, there has to be this group CH3, CH, then OH here. Okay, there has to be that group. If there has to be that group, these are how many carbons? They are 5. In fact, let me write this one here like this. Let me put H here and then the OH. This group has to be available. So it doesn't matter whatever you're having here, but so long as this group is available, then you are going to get that yellow precipitate, which is the triiodomethane. So that means here we can have the CH2, CH2, and then CH3. Not so? How many are they? 1, 2, 3, then 4 and 5. Those are 5 carbons. And then oxygens, of course, we are seeing 1. And then hydrogens, these are 3, then plus 2. That is 5, then 7, 8, then 9 plus the 3. That will be 12, which we are having there. So that is 1. But then this one here, when you look at this carbon here, it's a chiral center. This group here, hydrogen, is different from the methyl, is different from the OH, and it is also different from this propyl group. So that means here we are going to have optical isomerism, okay? Because they said we consider stereoisomerism and then structure. Now for structure, I can use chain, whereby I can get this one here, I cut it off, and then I put it here, okay? So that means I'm going to have something like this. This is CH3, then again C, then OH here, then you have hydrogen here, and then you are still going to have this C, and then you have the CH3. Remember, this one has shifted to this, okay? Then a hydrogen here will rearrange and then it comes to that one there. So what are we going to have? Now the CH2, which is here now, is going to become CH what? 3. Are we there? Then this carbon here has a hydrogen, because they were 2. So it is remaining with 1. Now this one here is still a chiral center, but this one is not a chiral center because it has 2 methyl groups. Are we there? Okay, so that means this one has 2, and also this one has what? 2. So there are 2 optical isomers here, and there are 2 optical isomers here. So that means the total then becomes a what? A 4. So our answer becomes a C here. Question 33. An amine is produced in the following reaction. So we have, this is iodoethane, then plus ammonia, and then you get ethylamine, or we call it ethylamine, then plus an ammonium salt there with the iodide, okay? Ammonium iodide. What is the mechanism? The mechanism, we can see that this one is replaced with this. So that is a nucleophilic substitution. So that is a substitution, nucleophilic substitution. Actually, this one is like this. We have a C, then if this is the iodide, and then we have the 2 hydrogens here. Since group 7 elements are electronegative, iodine is more electronegative compared to carbon, so it tends to pull bonding electrons towards itself, and it attains a partial negative what? Charge. Then carbon seems to be losing the electrons, so it attains a partial positive what? Charge. Now ammonia here has a lone pair of electrons. Now this lone pair, because this one seems to be losing electrons, now this one is rich in electrons, so it supplies the electrons. You see that? And then from there, we can actually have this one going off. Then you get the CH3 here, then C, and then I can put here CH2, okay, then NH, maybe 2, and then I project one hydrogen here. But this one, because it has used its lone pair, then it will attain a positive what? Charge. Then it has to lose this one here. So what is happening is that another ammonia molecule actually will come here and then scoops off this hydrogen from here, okay? And then this one will break off by giving to that. Then you will get this CH3, CH2, then NH2, okay? So what are we having here? Ammonium ion. But again here, we are having an iodide that came from here. So this iodide, when it reacts with this ammonium ion, then you can get this ammonium iodide. You see that? By the way, we call this one nucleophilic. Philic means love. So nucleo, that is what is in the nucleus, right? And in the nucleus, we have protons and what? Neutrons. So these ones are positively charged. Here, there is no charge. So what loves the positives must be the electrons, which are negatively charged. So that species which is rich in electrons and donates the electrons is what we call the nucleophile. Okay, so this one is a nucleophile. It can be a negatively charged ion, just like the OH here, okay, or just a molecule like this ammonium here, and it has a lone pair of electrons, then it can donate. Okay, so that is that. Then question 34, the reaction shown can be used to lengthen a carbon chain. Yeah, that is when we use the cyanide. So it is also nucleophilic substitution. So this one comes here, replaces this bromine there, and then you see. So I can oxidize this one, then I get a carboxylic acid, and then I put other conditions to get whatever I need. Which row shows the correct rearrangement and conditions for this reaction? Now, the cyanide here must be in a solvent called ethanol, okay? So we can have potassium cyanide, okay? Then in ethanol, look for ethanol. You're seeing it here, okay? And here. But usually we are using potassium cyanide, then in ethanol. Where we are using hydrogen cyanide, it is when we get ketones and maybe aldehydes, in other words, carbonyl compounds, reacting with hydrogen cyanides, and then we get what we call hydroxynitriles. We get something like that, then an alkyl here, and then an alkyl there, okay? Hydroxynitriles. That is when we are using hydrogen cyanide, okay? Now, for this one here, it has to be potassium cyanide or sodium cyanide in ethanol. So the answer has to be a B, okay? Question 35. Which row shows the products formed when cyclohexene reacts with acidified potassium permanganate under different conditions? So here they are giving us when it is cold, dilute, and acidified, and then here when it is hot, concentrated, and acidified. So here we have to look at the reaction of alkenes. So cyclohexene is actually like this. So when this acidified potassium permanganate is cold, dilute, okay, and acidified, then we are going to have a diol. We come out with a diol. So for A here, I mean for whatever is here, we have to look for a diol. Here there is a diol, but here there is no diol, no diol, no diol. So that means our answer actually has to be A. But let's go to this one here, hot, concentrated, acidified potassium permanganate. So we have to, this bond here is broken completely, and then oxidation takes place here and then here, okay? So what are we going to have? What is going to happen is that we shall get here the carbon oxidized here, it will go to a carboxylic acid, okay? So here there is that, there is this one here, then here, and then here, then here, and what do we have? This is 1, 2, 3, 4, 5, 6. So we shall also have a carboxylic acid here. Okay, so when you try to spread it, there is this one here and this one, and then we have how many carbons? 1, 2, 3, 4 that are left. So we have 1, 2, 3, and 4. You see that? So that simply means that our diagram here is correct. So this is what we get under the oxidation when it is hot, concentrated, okay, and acidified. So this is it. So our answer has to be this A here. I don't even need to look at anything else. This is a DIO. We don't get a DIO when it is hot concentrated. You see that? I don't need to look at others. Question 36. 2 steps in the free radical substitution reaction between methane and chlorine are shown. So we are seeing a radical here reacting with a molecule to produce another molecule and then a radical. This one is called propagation. Okay, propagation reaction. And then we are seeing a molecule here again reacting with a radical. Then after the radical, we get a new radical and then a molecule, a new molecule. So that is also propagation. Okay, so even this one is propagation. Now look at what they are asking here. Which statement is correct? Part A, option A, step 1 is initiation and step 2 is propagation. No, that is out. Initiation, we see chlorine as a molecule, okay, breaking homolytically. So it breaks like that, and then you get the 2 radicals. Then the radicals here will attack a molecule, okay? They will attack that organic molecule, and then they produce another molecule, then another radical. Now propagation is there. So this is initiation. Okay. Now, step 1 is propagation. Step 2 is termination. No, termination, that is when we have 2 radicals. Let's say this one here, then plus another radical, and then we get the CH3Cl. So this is termination. You get that? So step 1 is initiation. No. Even now for D, both steps are propagation, and indeed we saw them as well, propagation. So that means our answer here has to be a D. As simple as that. Question 37. Compound P displays cis-trans isomerism. This is actually geometrical isomerism under stereoisomerism, because we have stereoisomerism. Under that we have geometrical and then optical. Okay. And gives a red-brown precipitate with failings solution. That means we must have an aldehyde. There has to be an aldehyde, because it is the one that gives a positive test with what? Failings solution. So here there is no aldehyde. This is actually ketone here. So this one is out. Okay. We can see an aldehyde here, an aldehyde here, and an aldehyde here. But if it is cis-trans, then the 2 carbons that are in the double bond must be having 2 different groups attached to them. When you look at this one here, it has 2 hydrogens attached to it. So this one fails. You see that? Already this one is out. Then we go to C. Again, this one has 2 hydrogens attached to it. So it will fail. That means the answer is here, because this one has 2 different groups, and also this one has 2 different groups, and it has an aldehyde which can give a positive test with failings what? Solution. So that means our answer has to be a D here. Okay. Then question 38. Fructose is a sugar with more than 1 chiral center. The fructose molecule is shown with X, Y, and Z, indicating 3 carbon atoms. And this is what we are given. But let us identify a chiral center, okay, from here, because they are saying which carbon atoms are chiral centers. Remember, chiral center is the one that is connected to 4. It's that carbon atom connected to 4 different what? Groups. Look at this X here. This group here is different from this, is different from this whole group here, and is different from this whole group here. That means this X here is a chiral center. Then we go to this one here. This group is different from this and is different from this whole group, as it is different from that whole group. That means even that one is a chiral center. So X and Y are chiral centers. Now let's go to which one? Let's go to Z. So Z here, we are seeing a hydrogen and a hydrogen. Those two are identical groups. So that means this carbon here labeled Z is not a chiral center. So we are looking for X and Y only. So that means the answer is B. Question 39. An organic compound T contains only one functional group. Compound T has empirical formula. This one here, C2H4 and O. Some functional groups are listed. We have alcohol, we have aldehyde, we have ester, we have a ketone. And then what else are they saying? Which functional groups are possible for compound T? Now, if this one is an empirical formula, that means we can multiply with any other number. Suppose I get this one here, okay? Suppose I get this one here, and then I multiply by 2, because this is empirical. Now, to get the molecular, we can have something like C4, then H8, and then O2. So this one can be CH3, CH2, CH2, how many are they? OOH. So what do we have here? 3, 5, 7, 8 hydrogens, right? And then the carbons are 4. Then oxygens are 2. So, but this one is a carboxylic acid, okay? Carboxylic acid. But amongst these functional groups, we don't have a carboxylic acid. Now, I can transform this one into a compound from here that has gotten 2 oxygens, for example. That one can be an ester. And then I have something like CH3, maybe CH2, maybe C, or then OCH3. Okay, this is an ester, not so? So if this one is an ester, then we can see it here. You see that? Now, I've multiplied by 2. Any number that you're going to multiply here is going to give you more oxygens. Are we there? Now, like we multiply by a 2 and then we got 2 oxygens here. An alcohol must have 1 oxygen, not so? Like maybe you're having CH2 and then OH. Or it is CH, maybe 3, and then you have something like OH here, and then you continue. You see? So an alcohol has only 1 oxygen. Okay? So that means, and by the way, if this is an empirical formula can be the same as the molecular formula. Now, if this is the empirical formula, can I convert it into a molecular formula? This is CH3, maybe CH2. Okay, these are 2 carbons. Suppose I say CHO. How many hydrogens do we have here? These ones are 4. This is ethanol actually. These ones are 4, and then 1 oxygen, and then 2 carbons. So now you can see that this is an aldehyde. Okay, this is an aldehyde. So from this formula here, we can see an aldehyde, which is the same as, it's a molecular formula, but it's also the same as the empirical what? Formula. So that means an aldehyde is okay. Okay? So from here, by looking at just the empirical formula, equating it to the molecular formula, we cannot get what? An alcohol. Okay? Because if these are 2 carbons, the alcohol that is coming from there is ethanol. So it is going to be CH2, then OH. And the hydrogens are going to be 6. They are not 4. You see that? So an alcohol is actually off. And I told you, another reason as to why the alcohol is off, I can get this molecule here and I multiply with any number. So if I multiply with 2, I'm seeing that the oxygens are 2. An alcohol cannot have 2 oxygens. It is going to have, okay, 1. Okay? And they said only 1 functional group. So it can have the two oxygens if it is a diol, but yet they said only 1 functional group. Do you see that? Then how about a ketone? This one cannot be, if we, let's say, multiply this one by, let's say a 2, okay, maybe a 3. When we multiply by a 3, a ketone, first of all, is supposed to have, let us consider how a ketone is supposed to look like. This is, let's say, a CH3. Then the simplest ketone is propanone, okay? This is the one here. These are 3 carbons, okay? But here we are having what? 2. Now to get a 3 from here, we shall multiply by what? By 1.5. But usually the number that we multiply in the molecular, in the empirical formula to get the molecular formula has to be a whole number. You see that? So if you put any whole number, let's say we want to get a whole number here. So if you set 2, you will have this one here. But remember, you are getting what? 2 oxygens. You see that? If you multiply by 3, you are getting 3 oxygens. You see? So that one is not going to give us a ketone, like one functional group. So that means even a ketone has to be off. So a ketone being off, then that means our answer is on 2 and 3, which is actually what? A C. Question 40. The mass spectrum of an organic compound has the following features. The molecular ion peak is at mass to charge ratio is 60. This peak has a relative intensity, that is the relative abundance, at 100. And then there is a peak at 61 here, which has a relative intensity of 2.2. Now let's do something here. The moment they give you these relative intensities and then the values of the masses of the peaks here, you are supposed to use this formula here. We use it when we are finding the number of carbon atoms, okay? So number of carbon atoms, number of carbons is going to be equal to, we get 100, then divide by 1.1, then times the relative abundance of the m plus 1 peak, then divide by the relative abundance of the m plus what? Peak. So this is going to be 100 over 1.1, then times, if the molecular ion peak is at 60, so this one is at 60, then this one is at 61. So 61 is the same as, if this one is m, then this one will be m plus 1. Are we there? So I'm going to use those 2 there. So for the m plus 1, they have given us the relative intensity as what? 2.2. So I'll put 2.2 here. And then for this m here, we are having what? 100. So I'll put 100 here. Of course, this one will cancel with this. 2.2 divided by 1.1, we shall get 2. Now, that means when I come to my options here, I'm supposed to look out for the compound that has gotten 2 carbon atoms. And I'm seeing them here. First of all, these ones are how many? These ones are 3. Then also this one here. And this one is off. Now, amongst these 2, which one has its MR as 60? Okay. So we have to look at the MR of, let's say, the first one, which is methanoate, not so. This one is going to give us how many carbons? There are 2 times 12. Then hydrogens, how many are they? They are 4 times 1. And then oxygens are 2, then times 16. This one will give us 24, then plus the 4, and then plus the 32. So this one will give us 36. 36 plus the 24 gives us 60. Now let's look at the MR of ethanoic acid, CH3COOH. Now this one is going to give us 2 carbons times 12. Then we have 2 times oxygens are 16. Each of them is 16. And then hydrogens are 4. So 4 times 1. We shall have 32 here, just as here. Then we have 24 just as here. And then also 4 just as here. So it is also giving us what? 60. Okay. Now we continue with this information that is given here. They are saying there is no fragment peak at 17. 17, if I get this one here and I fragment it, this one is going to give us the 17, the OH. Are we there? But this one here, because there is a possibility of this one giving us the 17, because it's the OH. O is 16 and then hydrogen is what? Is 1. But then when you come to this one here, it is H, then C, then double bond to that, and then we have O, and then CH3. So there is nowhere we are fragmenting and then we are getting a 17, because fragmenting here, you can get this. You see that? That is a 12 then plus 1, that will be 13, plus 16, that will be like 29 also. There is fragmenting here, maybe plus this one here, so like that. So the 17 can only come from the OH, from ethanoic acid. So that's why we are going to take it off from here, okay? And then our answer will become A, as simple as that, okay? So this has been it for this paper. Thank you so much for watching. May God bless you. If you find the content very helpful to you, kindly like, share, and even subscribe. See you in the next videos.